out and go through, again, I'll go through a specific case, is the Kepler problems, I guess, where we have some central force and other various bodies orbiting it. So, and they also mention, I think, geodesic equations on like a two-dimensional surface of revolution. But yeah, I'm going to focus on Kepler one because I understand that one a little better once we get to the actual equations. Right. So anyway, this. So we have this is a local diffeomorphism, which then implies, yes, by the inverse function theorem that this is implies that this is invertible in some region, and so implies by the inverse function theorem that f1 x of p is also a local diffeomorphism. Why? Essentially, they say, I guess, because there is they define a matrix between the two of them, where they define the matrix p squared
dx dt.
They say that that matrix is invertible because that's a local diffeomorphism, and that implies that f1 is invertible too, because
yeah, because it's second derivative. Yeah.
Okay. So f1.
Well, the second derivative is d of 1 by dx and d of 2 by dt, and that's why it's equal to the same thing. That's why. Well, what you do, you look at that map. Of course, this is a little bit too advanced at this point if you didn't take geometry. But you look at, say, map F1. It maps 2n variables to 2n variables. You need to, it is local diffeomorphism is the Jacobian is not equal to 0. So you need to compute the Jacobian on that. So you need to take, well, call these variables y. You need to compute all these derivatives. You get the matrix, 2n by 2n matrix. And it has to have a non-zero determinant. And the same with F2, when you compute it, in one block of that, it will be 2n by 2n, and it has 4 blocks, n by n. Okay? And so one block of that will be the second derivative of phi. And it will appear the same block in F1 and F2. Well, if you try to do it, I mean, you can do it. It's not really like anything. Well, let me just show so that you're not confused that much about this. There's nothing really. But, well, here is a map, right? Well, let me write it in indices. So you have xi, pj, and you map it to this, which is dphi by dpi, and then pj or pk. Okay. So what is the Jacobian of that? Well, let me call this y k. Well, yeah, it doesn't matter. So you take this and you differentiate it with respect to both of these variables, and then you take this and you differentiate it with respect, right? So that will be like 2n by 2n, where these are all n by n matrices. So we'll take that and differentiate with respect to x. You get d2 phi by dx dp. That's that matrix. Then you have these, well, derivative by that. You get d2 phi by dp dp. Then dp by dx, well, that's 0. And then dp by d, that's basically the unit matrix. And then you compute the determinant of that. Because of that 0, the determinant of this product minus this, well, this is 1, this is 0, so it's just equal to that. So it is equal to the determinant of 2n n by n matrix of this one. So if this is not equal to 0, well, that is not equal to 0, and then it's local diffeomorphism. If you look at this map, this matrix will be different, but it is equal to the same thing. Well, look at this now. So, do you need that?
No.
So here you have xp, well, let's say xi pj, and then you have xk, and then dphi by dx, let's say n. Well, n is L. Okay, and so then the Jacobian will look like this. You take this and you differentiate with respect to x. You get delta, which is the identity complex, right? Then you take dx by dt, that's 0. Then you take this, differentiate with respect to x. You get the second derivative, dx dx. And then dt by dx by dt, so you get dx dt. So that's the Jacobian of this map. And if you take the determinant of that again, because of that 0, it's this minus that, so it's just equal to the determinant of this matrix. And that is the same as this. So if this is not equal to 0, then that is not equal. If this is local diffeomorphism, then this is also local diffeomorphism. Is that clear?
All right, well, that made perfect sense. So, going from that, so we have that both F1 and F2 are local diffeomorphisms. Then we also have the map defined between them, C, which we can then say that, yes, C is also, so because of that, C is also going to be locally defined as a diffeomorphism by D of x equals, so
you missed phi, they both.
Oh, I did. So then once we have that,
is it P? Second component? Yeah, it must be P.
Oh, yes. Sorry. Did I write that? Okay, no, I didn't write it wrong. My notes says to write it wrong. All right, so they then say that we can kind of redefine this as, I guess, essentially a change of coordinates, so that we have C of QP equals x to C. So just associating that and that term with, well, I guess that was already associated with that, but the term, associating dp of phi with q, which I think is our position, if we interpret this as a physical system.
Momentum.
Oh, so q's momentum?
Q, well, the first one is position.
Okay, yeah, and then p's momentum. Okay. Just making sure I have that down. All right. All right, so they defined the C to be the canonical canonical transformation with the generating function of phi. Yes. So from that,
so what does the word canonical mean?
Very individual canonical forms. I can't remember the general definition. Standard, I guess. Standard.
Well, yeah, but standard, kind of legal almost, yeah. Well, in this sense, canonical means that you have two n variables and you transform them in other two n variables. And, well, first of all, it must be a local diffeomorphism so that you can invert it. And then I think the symplectic form has to be invariant of the same.
Yes, they mentioned there that the symplectic form is preserved.
That's the definition of canonical.
So from that, they then say that generally we can use C to map a flow in the, so map the Hamiltonian flow in the x to C plane to a new Hamiltonian flow with slightly different functions u hat or u tilde j in the T plane.
What is u tilde?
That is, I think, that is just the new functions that are transformed. I think the functions are more or less the same, but I think something gets slightly changed. Not sure what, unfortunately. Well,
Here's the definition in the paper.
yeah. Hmm?
Here's the definition of utility in the paper.
Oh, it does it. It's about right there. Right, see the lines. Where, yes. Utility of J